All right, so questions. How'd the ODP come out? Good? Awesome. Cool. So I think I'm done with ODPs until Monday. So you got a break. Yay, good work. So let's keep talking about standard in and standard out and how we can do different things with the input to programs or the output from programs. And we've talked a little bit about quotation marks, right? So we're talking about Bash now, not C, for a few minutes. In Bash, we can put something inside double quotes, right? And it will let us do things like, write special characters like a single quote, and it won't get confused. But if we have a variable like $x, it'll go ahead and it'll say, oh, this person wants the value of the variable x, and it'll go ahead and substitute. So the quotes don't stop the dollar signs from being treated like dollar signs, but it'll let us do things that would otherwise potentially get us in trouble, like echo don't go in there. And it's confused because it thinks that single quote started a string, and it's waiting for me to end it, right? So you can say, put it inside double quotes, and that works fine. And if you have dollar signs, it goes ahead and it replaces them with a value. Single quotes, on the other hand, kind of suppress most characters. They really kind of turn this into a literal string. And so $x just comes out as a $ followed by x. So if you just want to print something out, you don't want to do substitutions, right? You can use single quotes. If I say echo asterisk, instead of printing a star, it gives me a list of my files in my current directory. And why does it do that? Because the shell takes that asterisk and it says, oh, this is a wildcard. Let's replace it with a list of files in this directory. So if I say echo star.mp4, it shows me a list of files in my directory that contain mp4 at the end of their file name. And if I echo double quote star, that just gives me a star. And if I echo single quote star, that just gives me a star. So double quotes and single quotes are different levels of suppressing this behavior of expanding things that you're trying to echo. Steam. Yeah, gotta have steam. So the other kind of quote is a back quote. Okay, and back quotes on my keyboard, they're in the upper left, they're right below the tilde key. Okay, a single quote is usually on the same key as a double quote, and it's kind of a forward quote. Back quotes are different. Okay, we don't usually use them when we're typing things, it seems, but they have a really powerful meaning inside a bash shell. So I can say x equals cat, or sorry, let's say x equals date, and I can echo the value of x, and it's the symbol date. But date is also a command, right, which shows me the current date and time. So here's what I can do. X equals back quote date, and now if I echo $x, it's equal to the output of that date command. So when I said x equals back quote date, it actually executed this command date. It captured everything that it sent to standard out, and it set x equal to all of that output. And if I look at x again, right, it's not the current date and time, it's whatever it was when that date command ran when I said back quote date. So So if I want a symbol that shows me what my current directory is, I can say my dir equals back quote, print working directory, and now my dir is whatever my directory was. So inside a bash script, we can execute any command we want and store its output in a variable and then start using that in if statements, echoes, etc. Yeah?
Are there two back quotes around date and PWD?
Yes, you need one in the beginning and one at the end. And I think if you don't have one at the end, then it gives you this continuation prompt which says, I'm waiting for more input. So this is potentially pretty useful. Right, so here's the C program that generates some output. If I set x equal to back quote output, x is a symbol in bash that contains the output of that program. So this thing in back quotes can be basically anything executable. Could be a shell script, could be something weird like a VI command, but that gets really strange. But it's fun to play with. All right, so we can execute commands inside bash and we can capture the output instead of having them appear on standard out. And that can be useful. All right, so let me give you a few other commands and then we'll start putting these together. Really useful command is grep. Grep is a search command. And the format is basically grep followed by something you're searching for, some search pattern, and then the file in which you want to search. So for example, let me make a copy of my bash RC in here. So got a bunch of stuff in here. Suppose I want to know all the things that I alias inside my bash RC. Right, I can say grep alias bash RC, and it'll pull up all of those statements that contain the word alias anywhere in them. Okay, usually alias is in the beginning of a line, but if it was anywhere in the line, it'll pull that up. Well, I do a lot of aliasing.
Was that dot bash RC?
Yeah. Yeah, so that's a good reminder. Home directory, you have a file called .bash RC. This file gets executed every time you start a bash session. So you can put any commands in there that you want, and each time you start your bash session, those commands get executed. So you can set up aliases, things like that.
Yeah, because I try to do the alias without going there.
Yeah.
Every time you close the terminal, it will go away.
Right, yeah, if you just say alias,
There, it stay there.
if you just say alias at a prompt, it goes away once you exit. But if it's in bash RC, every time you start a bash shell, these commands get executed. It recreates those aliases for you. So I can put something in here that says, hello, Nick. And the next time I start a bash shell, it says, hello, Nick. All right, so you can put whatever you want in there. right, so here I want to see every line in my file that contains an ampersand in it. And there's some things where I have if statements with an ampersand in the middle, and so on. So it's just a search function. But the cool thing about grep is that this pattern doesn't have to just be a set of characters you're looking for. It can be something much more general that we call a regular expression. And that's the RE part of grep. And we're going to talk about regular expressions later, because it's a whole topic in itself. But it's another one of these things that you can live without knowing, but if you know it, you'll find lots of ways to use it. And it lets you do pretty elaborate searches for things. And eventually we'll see that it lets us also do substitution of one thing with another. And it's a great tool for editing files, and it works inside VI. So anything you learn about regular expressions helps you with editing and so on and so forth. All right, so grep is a useful command. Another command is sort. So you can say sort and give it the name of a file, and it'll sort it for you. So it sorts it according to ASCII ordering, and it's kind of silly on a shell script to sort it. But you know, my aliases came out first, and there's some else's and some esacs, which is the end of case, and exports, and then some fees, and so on and so forth. Alright, so there's a file. We can sort it. And it basically just alphabetizes it. There's another command which is called unique, U-N-I-Q. And unique looks for unique lines in a file. Basically, it goes through a file, and each line it says, is this the same as the previous line? And if it is, it will not print it. It will only print the first time that a line occurs. If it's followed by copies of itself, it will suppress those. So if I say unique file, I almost get back my original file, because even though this is a file appears twice in here, it's not successive. So this is a file is followed by cool stuff is followed by this is a file. Those are different lines, right? But down here I had by followed by, and so when I said unique, it only printed out the first occurrence of by. Now suppose I want to know how many unique lines I have in this file. Here's what I can do. I can sort file and pipe that into unique. And now, since it's alphabetized at first, all the occurrences of cool stuff were next to each other, and it only printed out the first time it occurred. And I can take this and pipe it into word count, and now I know I have 7 unique phrases in my file. Now you could write a C program to do that, but that's a pain, right? So a few commands put together makes it pretty easy.
Those commands are C programs, right?
Those are C programs, yes. You can also say unique-C, and it'll tell you how many times each phrase occurred. Right, so I know that by and hello and this is a file occurred twice. And I could take this, and I could pipe it into sort. And now my most common phrases are at the bottom of this output. And if this was thousands of lines, right, I could find the most common phrase by just looking at the bottom of this. And if I pipe it into tail-1, it'll just show me the very last line. And if I pipe it into a program called awk, and I say a little awk program here, which is print $1, it'll just print out that first column, which is number 2. And if I say something like x equals back quote all of that stuff, x is now equal to 2. Do we need to do this every day in our lives? No. Right? But there will be a moment when you need to do something similar to this, right? And the more you understand this small kernel of commands and how to put these things together, and the more practice you've had with thinking about tagging commands together like this, right? Suddenly it becomes pretty easy to do some kind of intense processing with just a line of bash code, some back quotes. So we're going to talk about these more. We're going to spend a few days talking about awk towards the end of the course. It's actually a whole little programming environment, but it's useful for taking apart files or standard input and breaking it into columns. So I use this all the time when I look at grades, right? I look at the grades file for the ODPs, and it's got a username and a date and a time and some other stuff, and then at the end there's a score. 5:10 says you got 5 out of 10. And I can cobble together a single line like this and figure out exactly how many people have gotten 10 out of 10 on the assignment and how many people have gotten something other than 10 out of 10. And it takes care of multiple submissions and all that kind of stuff. And it's just file processing, right? So we'll play around with this stuff later and see that it's pretty useful. All right, so tail's a good one to know, right? Tail takes the last few lines of a file. If I just say tail file, it shows me usually the last 10 lines, but I can say tail -3 file, and it'll show me the last 3 lines. I can say head -number, and it'll show me the first n lines. And these are just ways that we can take large files and make them manageable. And we got the spinning circle of doom up here. All right. And those are just C programs, right? And they have manual pages, so you can check the manual page for head. Lots of different options. Right? Instead of printing the number of lines, you can print the first few characters with a C option, and so on and so forth. All right, so let's talk about, I don't want to talk about that. PA2 issues. Yeah.
What are some common issues people have?
For PA2?
Yeah.
The same ones people are having in this class. So this business of scanning your input, right? So you run PA2 with some argument, right? If that argument is present, you need to scan it, see if it's an integer, okay? Don't try to scan it unless it exists. And how do you know if it exists? You got to check argc, right? So if argc is exactly 2, then scan argv bracket 1. And I'm still seeing people who are trying to scan this even though argc might be equal to 1. And if you touch argv1 and argc is only 1, it's going to seg fault. Okay, so see if argc is 2. If it is, the person gave you a command line argument, scan it. If it's not an integer, game's over. If it's an integer but it's negative, game's over. Okay, if it's a nice positive integer, then you say, okay, we're going to play with 17 sticks, whatever the person specified, and you go on. If argc is 1, right, they have just said program name, so ask for the number of sticks. That's just a printf. read a line. That's f gets. And then scan it. That's s scan f. And now you're right back to where you were here. If the thing you scanned isn't an integer, or if it's a negative number, tell them that's illegal, game's over. Otherwise, you've got the number of sticks, go ahead and play. Right? And if argc is not 1 and it's not 2, it can't be 0 because it's always at least 1. So if argc is bigger than 2, what do we do?
Tell them,
Go to
Yeah.
ARC1.
I would just say game's over because they broke the rules. They're supposed to run it with one argument, which is the number of sticks. If they put multiple arguments on, that's not a recognized way to play the game. And I think it says that. If not, that's my bad. Let's see. Does it? Okay.
Does it?
It says that you have to take them out after an invalid initial input.
2 invalid initial inputs will register or game over.
That was the first.
That was the first one. Well, I don't have PA2 here. That's shocking.
The number plus.
It's online, but I can't get to it online.
And one of the points he said is there is exactly one such argument. So
Okay.
more than one you should be failing.
Okay.
I just have the page cached.
Good idea. All right, so getting those logistics lined up is definitely an issue that pops up.
So it's preferred that we exit if there's more than 2 argcs.
If argc is bigger than 2, tell them they should only have one argument, and you can exit right there. What else? Similar issue with how many sticks do you want to take, right? But if you've got this figured out, you can probably figure that out. But make sure you're allowing them unlimited tries for the number of sticks to take. Okay, so if they put in something other than 1, 2, or 3, remind them what their choices are and ask again, and just keep asking. Cool. Make sure on your output, right, you show a bunch of sticks and then show the number of sticks in parentheses after that. And that's just add a %d in parentheses on your printf and print that out. And everybody knows how to print sticks on the same line, right? Just don't put that \n and it'll stay. It'll continue on one line. Yeah.
Do we have to print out that it says like I take this number of sticks?
Something to indicate how many sticks the computer's taking, yeah.
Okay.
Doesn't have to be fancy, but otherwise you gotta subtract to like see. I gotta subtract to see.
So you
Yeah.
want print statements stating what the user and computer chose.
The user is going to say, 3 sticks. You don't have to repeat that. You can if you want. But when the computer decides I'm going to take 2 sticks, you should say the computer takes 2 sticks and then show the pile of sticks. And then how many sticks do you want to take? The user types in a number, show the new pile of sticks. The computer takes 1 stick, show the new pile, and so on. Yeah. And let me ask you not to put delays into your code. I won't ding you if you do, but sometimes it's nice to put in sleep statements so that the lines come out 1 line per second. That's kind of nice so that the user can read it while it's going, but it's a distraction when I'm trying to grade these. So I usually go in and I edit those out. So I appreciate the sentiment of it though, but if possible, go ahead and don't put those in your submission. But don't break your code trying to take it out. If it breaks your code, just leave them in. Don't ever make last minute changes to your code. having just said that. A lot of times you get something working and it's all looking great, and you're about to submit it, and it's like, oh, I forgot to put my name in it, right? So you go in, you type your name in the top, and you go ahead and submit it without recompiling it and retesting it, right? And I've had cases where the person, put in a single slash instead of 2 slashes for their name, and I try to compile it, and it says, syntax error, and now I got to debug your code. So if you make last-minute changes, always make sure you recompile and you retest, even if it seems like a really minor change, because typos come in, right? And I'll work with you on that, but it's good practice to make sure it still compiles. All right. Well, let's let's talk about files. All right, so I got some files in here. Let's pick on file. All right, so there's file. So I want to talk about links. So this file, if I say -i in my ls command, it shows me a number in the beginning of each line. Okay, this is something called an inode number. So an inode is just an internal identifier that the system uses to identify each file, right? So we call this thing file, F-I-L-E. The system calls this 4197764. Okay, that's the name of this file. And it calls stick the file 4197370. That's what it uses to identify it. And there's a structure somewhere that says, hey, when the person says FILE, this is what file they mean. And when they say stick, that's what file they mean. And everything internally is keyed off of these numbers. So this is really the ID of the file. So a link is a way to create another file that points to some file, right? To create a second file that points to a first file. And we can do this a couple of ways. We can say ln, that's the link command, ln old and new. So let's just say, let's link file to haha. So now I've got file and I've got haha. And if I cat file, it's got all that stuff in it. If I cat haha, it's got all that stuff in it. If I do an ls and I look at my inode numbers, file and haha have exactly the same inode number. They are the same file. I just have two things that point to it. Now I could move haha to my home directory. And now I've got a file sitting under here called haha. And I've got something sitting under my 224 subdirectory called file, and those are the same file. Right? Two things in totally different locations in my directory tree, but they both refer to the same thing. And if I remove haha, this file is still intact. So remove doesn't always delete a file. What remove does is get rid of a reference to an inode, and then if that was the last thing referencing that inode, it deletes the file from the drive. But if there's something else still referencing it, then that file persists. Now the other thing I can do is I can say, make what's called a symbolic link. So I can put in this -s switch. And this does something fairly different. So now I've got my file and I've got my haha. But haha has its own inode number now. It's got a character in column 1 next to these permissions of L instead of a dash, and the file name under an ls-l shows up like this. It says basically haha is referring to file. So if I move haha up one directory to my home directory, and I look at haha, it says haha is referring to file. And if I try to cat haha, it tells me there's no such file. Haha exists, but there's no thing called file in my home directory. And it has no idea that I originally linked it to this file right here. I simply created a symbolic connection between haha and something called file. Now if I move haha back into my 224 directory, and I cat haha in here, it says, okay, haha is actually just a nickname for file, so it'll try to cat file, and it finds that in here. And if I remove file, and I try to cat haha, it says no such file or directory. Why? Because it's referring to file. And if I recreate file, then I can cat haha and it still points to that stuff. Bless you. So I can remove haha and that's not going to have any effect on file. Haha is really just a symbolic connection. Right, it says when you try to do something with this file, go over and use this other file instead.
Why would you link something instead of just copying it from your file?
Because when you copy it, it takes more space.
Okay.
So if you have a 20 megabyte file and you want to be able to refer to it somewhere else or with some other name, and you copy it, it takes 20 more megabytes on your drive. And so here's haha. So let's go into file and let's change it. And now if I cat haha,
So
it's pointing to the same thing.
Stays.
Yeah.
Okay. Does it do that even if you don't do the symbolic link? If you just do
Yeah, if you do a hard link, which is the non-symbolic version, same thing, because it's actually referring to the same stuff on disk.
Okay.
So a little bit like what Windows calls a shortcut, right? Where you just sort of create something that references another file, but without a lot of the overhead. So how do files get stored on disk? What is a disk? How much do you know about disks, like hard drives?
It's physical storage.
It's physical storage. They're cheap. They're really cheap. So here's an old school hard drive. Most stuff is flash these days anyway, so. But old school version, you have this metal disc that's spinning, 7,200 times per minute inside your laptop, which is pretty cool. And why is it spinning? Because there's something sitting over here called a read-write head. And so this is covered with a ferrous material. You can record north-south, south-north, little dipoles, little magnetic fields at different places on this platter, and you use that to store ones and zeros. So when you have a 2 terabyte drive, it's got 2 trillion times 8 bits. 16 trillion locations on here where there's these little tiny magnetic dipoles, each one which can be set, pointing up or pointing down to store a 1 or a 0. And this thing's spinning around all the time really fast, 7,200 RPM. And you have this read-write head. Well, this read-write head can move towards the middle or away from the middle, but it doesn't usually move around the disk. It's in a fixed position. So when you want to read something from this disk, you basically move to the right position and you wait for the thing that you're trying to read to eventually spin around and appear under your read-write head. And as soon as it gets there, you check that bit. You say which way is this magnetic field set up, and that tells you if there's a 1 or a 0. This stuff actually works.
So does that mean that like storage size for one of those hard drives is either based on density of like how many rings are fit within the cylinder or how large the cylinder is?
Yeah, and it's usually density because the size of these things is usually standardized. So there's, you said tracks, there's a bunch of tracks on here, right? Concentric rings. And if you have a piece of data sitting right here, you move this read-write head in so that it's positioned over this track. And you wait for this thing to come around over here. And then you sense it. And there's your bit information. And if you want to write, you do the same thing. You wait till the thing that you want to write is under here, and then you apply an electromagnetic field to set the magnetic dipole the proper way. And we usually think of this as broken up into sectors. So 8 sectors would look like this. And that's where all the stuff on your computer gets stored, right? It's crazy.
How does that compare to a solid state drive?
So solid state drive, we don't have moving parts. Well, we have electrons, but we don't have a spinning disk, right? So it's not as high density, and it's nowhere near as cheap. But we don't have to wait for the bit that we're interested in to move into this position. And we don't have to wait for the delay that it takes to move this read-write head forward and backward. So the startup time to do a transfer, if you just wanted to read a single bit, this is really expensive, okay, milliseconds. Once you've got everything in position and this bit is under the read-write head, if you want to start sucking in consecutive bits, that's really fast, okay? But the time to actually get here is incredibly slow, so that's going to be a lot better on a solid state. Plus, you know, if you drop this, there's a chance that you're going to damage it. Now, most of these things have accelerometers inside. They know when they're falling because gravity disappears. And they'll do something like park this read-write head into a position where it's not going to do any damage if it bounces on the platter. Right? So there's all this kind of stuff. Solid states, that's not a problem. Reliability, I think the jury's still out. Hard drives have gotten pretty dang reliable. Right? 5 years is not unusual. I don't know what the reliability of solid state drives are. I haven't used one long enough to have it fail on me. But probably the biggest difference is expense. Because 4 terabytes at Costco is like, you know, $100-some.
So you said that the reliability for them is like the same. I was thinking like for the solid, like for the disk, not the solid state, wouldn't there be a higher error rate? And like, because as it's moving, there's heat being added to it. Wouldn't that cause some kind of like magnetic drift?
Yeah, so historically, these kinds of drives were pretty fragile. The school I went to, this was in the 80s, the whole computer machine room, right, was a sterile environment. Typically, these things were about 100 to 1,000 times more sterile than an operating room, just in terms of air filtration, things like that. And the hard drive was 200 megabytes, and it looked like a washing machine, right? And you had to go in there, you had to shut everything down, lift the top up, and you had this special plastic container that you would lower on top of the drive, and you'd spin this thing to attach it, and then you'd lift it out, and it was like a cake serving tray, right? You'd put the bottom on it, and that was your hard drive. And it was a really scary procedure because sometimes something would mess up and your drive would get corrupt. So historically, these things were kind of fragile, but the reliability now is just phenomenal. I mean, I throw this thing in my bag and I carry it around, or I'll throw it on my bike and bounce over roadways and stuff, and it's like, it just seems rock solid. When solid state drives came out, there was some concern about how many times you could read and write a location. And the word was that, you know, you could only do this 100,000 times before you'd lose the ability to store information. That doesn't seem to have been a problem. And people use solid state drives just as a regular hard drive now. So it's an interesting area of technology. This is the thing that's really driven computer development, though. One of my professors said it should be called ferrous oxide valley instead of silicon valley. Because ferrous oxide, the coating of these things, this has really been where the breakthroughs have been. And it's the storage capacity that's really kind of driven the whole industry. Not that silicon is not important. I also had a friend who in the 70s was working on storing music digitally, and, you know, early compression schemes long before MP3 and stuff. The reason they didn't take it commercially was they didn't envision what was going to happen with storage. And they realized, you know, it would take megabytes to store a song, and they're like, well, that's never going to happen. You can't carry a megabyte in your pocket. So don't ever doubt the future. All right, so these inode numbers ultimately link to go to this track, go to this sector, and there's usually multiple platters in some form, virtually or physically, right? So go to this platter, this track, this sector, and this many bytes into that sector, you'll find the beginning of this file, right? And there's just structures inside Linux that keep track of all of this stuff. That say, here's my inode number, tell me where to find the file on disk, and it'll point you to that information. And then there's big complex programs that basically control this and say, okay, give me the contents of this file. And we don't have to worry about it. We just say fopen, we say fgets, we say fclose, right? So we'll play with those later. All right, so tomorrow I want to start talking about GDB. That's the debugging tool for C, and that's going to help us with going inside our C code while it's running, trying to find problems with it. So we'll start that.